A saturated liquid R134 at 55 degrees Celsius is throttled in an expansion valve such that the temperature of the two-phase liquid vapor mixture at the exit of the valve is at 0 degrees Celsius. The exit of the valve has 60% liquid by mass, that is Drainis fraction is given, and we have given the property at 0 and 55 degree, that is enthalpy of saturated liquid HF, while the specific enthalpy of saturated liquid, that is HFG, specific entropy of the saturated liquid, that is SF, is given at 0 degrees Celsius and 55 degrees Celsius. We want to calculate the specific entropy of the mixture at the exit of the valve. So we can represent the throttling process on TS plot. So throttling is a basically irreversible process from high pressure to low pressure, and during this the entropy will increase. So this one is point number 3 and this one is point number 4. So 3 to 4 is the throttling process. At point number 3 we have temperature equal to 55 degrees Celsius, and we have the two-phase mixture at 0 degrees Celsius. So you have to collect the property at 55 and 0 degrees Celsius. And he says that it is a 60% liquid by mass, means 40% by vapor. So dryness fraction at this point is 0.4, 1 minus 0.6. And we are given the property of R134 at 0 degrees Celsius and 55, that is HF is given, and you want to calculate the specific entropy of the mixture at the valve. So we have specific entropy at point number 4, S4 equals to SF plus X4 into Sg minus SF at 0 degrees Celsius. So dryness fraction is known to us and value of SF is known to us. So at 0 degrees Celsius we have SF equal to 0.2044 and we are given SF equal to 0.4654 at 55 degrees Celsius. So this value is SF value is 0.4654. Now here we don't know basically the Sg value, but he has given the value of HF at 0 and 55. So we have HF at 0 degrees Celsius is 51.86 and we have HF is 131.3 kilojoules per kg. Enthalpy at point number 3 is same as enthalpy at point number 4, that is known to us. This value of 55 is same as H3 value and H3 is same as H4 value because 3 to 4 is a isoenthalpic process. So H3 equal to H4. Now this time, since we are knowing the value of H4 and H4 is a weight, we can write HF plus X4 into HFG. H4 is known to us is 131.3. Now this value you have to record at 0 degrees Celsius because point number 4 at 0 degrees Celsius. So HF at 0 degrees Celsius is 51.86 plus 0.4 times HFG. So from this we can very well calculate HFG value. So this value come out to be 198.6 kilojoules per kg. Now recall here we already defined the SFG. SFG is basically HFG divided by Tsat. So we can calculate SFG at 0 degrees Celsius. HFG is 0 degrees Celsius is 198.6. Temperature is 0 plus 273 in Kelvin. So this value of SFG come out to be 0.7274. Once we know SFG, we can use our first equation and we are able to calculate the S4 value. SF you have to use 0.2044 and Sg minus SF is same as SFG. So we have S4 equals to 0.2044 plus 0.4 into this value is SFG value is same as 0.7274. Solve this value. We will get entropy at point number 4 is 0.4953, that is kilojoules per kg per Kelvin. An ammonia ice plant operates between a condenser temperature of 35 and evaporator temperature of -15 and produces 10 tons of ice per day from water at 30 to ice at -5. We are working fluid is ammonia. Maximum temperature is 35, condenser temperature, evaporator is -15. We have 10 tons of ice per day from 32 degrees Celsius water to -5 degrees Celsius. And we are using simple cycle and we are given the data. So first of all, we'll draw here plant. We have a throttling valve, we have evaporator and a compressor. Condenser temperature is maintained at 35 degrees Celsius. Evaporator is maintained at minus 15 degrees Celsius. We want to produce the ice here. So the heat must be removed by the evaporator from the ice. That is a cooling load. And we will draw the graph on TS plot for water here and ice. So this is water or liquid and this one is ice. We have to cool down the water first from 30 degrees Celsius to 0 and from 0 degrees Celsius to minus 5 degrees Celsius ice. So process can be represented as a constant pressure line. So initially we have water at 30 degrees Celsius and finally we have ice at minus 5 degrees Celsius. So this one is sensible cooling process, sensible process, and this one is latent process. For latent process, HIF is given to us, that is equal to 335 kilojoules per kg. So value of HIF is 335. We want to produce 10 into 1000 tons of ice per day. So mass weight of water is known is 10 multiplied by 1000 divided by in 24 hours means 24 multiplied by again 3600. So this will become kg per second. So from this we'll calculate delta H and then we calculate cooling load. So mass of water circulated per kg second is 0.1157. Next we'll calculate the cooling load to cool the water from 30 degrees Celsius to minus 5 degrees Celsius. So we have cooling load, mass weight of water. First of all we have sensible cooling here from 30 to 0. Phase is water, so we have CPW 30 minus 0 degrees Celsius plus we have phase change at 0 degrees Celsius, so plus HIF plus we have sensible cooling of ice, so CP of ice from 0 degrees Celsius to minus 5 degrees Celsius. So it is 0 minus 5 is plus 5. So this total load is called as cooling load. So the mass of water here is 0.1157. This time some data was given to you. The CP of water was given as 4.18 and CP of ice is given as 1.94. So we have 4.18 multiplied by 30 plus 335, that is the latent heat of ice, plus CP of ice is 1.94 into 5. This answer will come in kilowatt because specific heat is kilojoules per kg per Kelvin. So cooling load is 54.39 kilowatts. Now this load is removed by the evaporator. So let's say this one is state 1, state 2, state 3 and state 4. So this cooling load is same as m dot into H1 minus H4. So the same cooling load is equal to m dot into H1 minus H4 and this time is the mass weight of refrigerant. We need to calculate H1 first. So he says that the cycle is simple. It means that the state at 1 is a dry and saturated. So H1 is same as Hg at minus 15 and his value is 1443.9. Now we required H4 value. H4 and H3 they are same value because it's a throttling process. So H4 is same as H3 is HF at 35 degrees Celsius. HF at 35 is 366.1. So finally we'll put all values. So this QL is known to us is 54.39. We don't know mass weight of refrigerant m dot r. H1 is known to us 1443.9 minus H4 is 366.1. So we can solve this and we can get the mass weight of refrigerant in kg per second. 0.0505 kg per second, but answer required is in hours. So we'll multiply this quantity by 3600. That answer is very close to 181.8 kg per hour.